What if an AI could not just write code, but actually reason its way through what seemed like an impossible problem, beating human champions at a major global competition?
That's quite the hook.
Right. Well, today we're diving into that exact story the moment Google's Gemini 2.5 deepthink achieved, well, gold medal performance at the International Collegiate Programming Contest, the ICPC.
Yeah, and look, this isn't just another flashy tech headline you kind of scroll past. The ICPC, it's often called the Olympics of Algorithmic Programming.
And for good reason, I gather.
Oh, absolutely, for very good reason.
Yeah.
I mean, picture this. Teams of 3 really brilliant students sharing just one computer.
One computer for 3 people. Wow.
Exactly, under a strict time limit facing these incredibly complex problems. But here's the real kicker, the sort of crucial detail.
Okay.
Only perfect solutions score.
Perfect. Like 100% correct.
Precisely. There's no partial credit, no, oh, that was mostly right, or good effort. It's absolute correctness and efficiency, or you get nothing. Zero.
That sounds brutal.
It is. That unforgiving perfect or fail rule, that's really the soul of ICPC.
And that lack of partial credit, that sheer difficulty, that's exactly why this AI performance is, well, it's pretty significant, isn't it?
It really is.
So our mission for this deep dive is to unpack what this win actually means. Is this maybe the ChatGPT moment for hard reasoning? The point where AI moves beyond just pattern matching or autocomplete.
To become a genuine problem solver.
Yeah.
Inventing plans under pressure.
Yeah, and executing them flawlessly. And what does this shift change for developers, for researchers, for basically anyone building complex systems today?
Okay, let's try and unpack this.
Sounds good. Where do we start?
Right, so let's talk about what actually happened at the ICPC. Gemini entered the contest 10 minutes after the human teams.
Started late? That's a handicap.
A big one.
Yeah.
Yet it just tore through 8 problems in the first 45 minutes.
8? In 45 minutes? That's fast.
Incredibly fast.
Yeah.
Then it solved 2 more within about 3 hours, hitting a total of 10 out of the 12 problems.
10 out of 12. Impressive. Yeah. And that performance, based on the standard time and penalty scoring, well, it translated to a second-place finish against the absolute best university teams on the planet.
Okay, second place is amazing.
Yeah.
But wasn't there something else, something even more striking?
Yes, and this is the part that really got people talking. Gemini produced a correct solution for problem C.
Ah, problem C. Okay, what's special about that one?
Get this. No human university team managed to solve problem C. Not one. Not during the entire 5-hour contest window.
Wow. Okay, so the AI solved something the best human competitors couldn't crack under pressure.
Exactly. It wasn't just fast. It solved the unsolvable, so to speak, within the competition constraints.
That's genuinely astounding.
It really is, especially when you think about the practical side. The ICPC format, it forces what you might call end-to-end thinking.
Right. You can't just solve part of it.
No, you have to carefully read and understand the problem, figure out a plan, actually code it, test it like crazy, fix all those little edge cases.
And then resubmit, hoping it passes all the hidden tests.
Exactly, all within minutes sometimes. This really rapid, iterative loop, understand, plan, code, test, refine, that's basically the working definition of Gemini coding under pressure.
And that's what matters for people shipping actual software, right? That whole cycle.
Precisely. It's not just some academic puzzle. It's like a compressed version of real-world engineering challenges.
Okay, so let's zoom in on that impossible problem C then. What was it actually about?
Right. So it reads almost like a riddle from a civil engineering exam, or maybe a really complex puzzle. It's all about optimizing fluid flow in a network of ducts and reservoirs.
Ducts and reservoirs.
Yeah.
Okay, sounds tricky.
The huge challenge is what they call the continuous and huge space of possible settings for all these ducts, like how much each one is open or closed.
So trying every combination is just out of the question.
Completely impossible. Way too many possibilities. Brute force wouldn't even scratch the surface.
Right. So how did Gemini tackle it then, if not brute force?
Well, this is where it gets really fascinating. The model didn't just try settings randomly. It fundamentally flipped the perspective.
Flipped the perspective? How so?
Instead of directly fiddling with the duct settings, which are super numerous and complex, it assigned priority values to each reservoir.
Priorities. Like how important each reservoir is.
Exactly. Sort of expressing how much that particular reservoir should be favored in the flow distribution. This change in viewpoint, this reparameterization, that was the key insight.
Okay, interesting. So it changed the variables it was optimizing for. Did that make it easier?
It unlocked the whole thing. Once it was reframed like that, the model figured out something critical. the objective function, the thing it was trying to optimize in this new priority space, it behaves like a perfect convex bowl.
A convex bowl. You mean like a smooth valley shape with a single lowest point?
Exactly like that. Think of finding the bottom of a perfectly smooth salad bowl, and that shape is absolutely crucial.
Why? What does the bowl shape let you do?
It means you don't have to search everywhere. You know there's only one minimum. It allows for this incredibly efficient search technique called nested ternary search.
Nested ternary search.
Ah.
Okay, what's that like?
It's kind of a zoom-in check method. You keep narrowing down the possible area where the optimum could be, cutting away huge chunks of the search space with each step.
Ah, I see. So you quickly pinpoint the lowest point without checking every single spot on the bowl.
Precisely. It turns this impossibly vast, continuous problem into something manageable, something tractable. It wasn't just clever coding, it was a deep mathematical insight.
That's really the core of it, isn't it? The abstract reasoning. It wasn't just spitting out syntax.
Not at all.
It was about the plan. The ability to, like you said, reparameterize the problem, spot that hidden mathematical structure, the convex bowl, and then pick the right super efficient search strategy for that structure.
That's the essence of high-level problem solving right there.
It really mimics how scientists and engineers often make breakthroughs by finding a new way to look at things.
It's genuinely mind-boggling stuff. So, okay, when we peek under the hood, what's actually powering this? What are the key capabilities inside Gemini 2.5 DeepThink that make this possible?
Right. Well, there are essentially three core capabilities working together here. First, there's what they call long horizon chain of thought planning.
Long horizon, meaning it thinks many steps ahead.
Exactly. It's not just thinking one or two moves ahead. It can map out a complex multi-stage plan and actually stick to it. If it finds a promising direction, it commits and follows through.
Okay, so it has focus. It's not just randomly trying things.
Right. Second capability, multi-agent parallel thinking.
Multi-agent, like a team of AIs.
Sort of.
Yeah.
Imagine several AI solvers working in parallel. They each propose different plans, they run code to test their ideas, they critique each other's approaches.
Critiquing each other, that's interesting.
Yeah, and then they merge the best improvements. It's like a collaborative synthetic team, all working towards the best solution.
Okay, that makes sense. What's the third one?
The third is reinforcement learning. But crucially, it's tuned not just on, scraped internet text or simple coding examples.
Tuned on what then?
On hard, noisy targets. Real-world coding challenges, like the ones in ICPC. This teaches it not just how to get the right answer, but how to recover when things go wrong.
Recover, like debugging its own mistakes.
Exactly. How to debug, how to learn from failed attempts, and how to reliably converge on a correct solution even when the path isn't obvious.
So, listening to this, some might still think, okay, maybe it's just throwing massive amounts of compute power at it. Brute force, essentially.
Yeah, that's a common misconception. But no, it's really not brute force. It's much more refined. It's what we'd call disciplined iteration.
Disciplined iteration. What does that mean in practice?
It means this constant, very efficient cycle. Propose a solution, execute the code, meticulously inspect the results. Logs, outputs, everything.
Looking for errors or inefficiencies.
Right. Then patch the code based on what it found, rerun it, check again, and eventually submit. Competitive programming just makes this loop incredibly visible and forces it to happen fast.
So it's learning and refining in real time, basically.
Exactly. Through that discipline cycle, it converges on something that works.
This whole win really highlights that difference between just remembering something and actually reasoning through it.
That's a great point. Remembering is often pattern recall, right?
Yeah.
Maybe tweaking something you've seen before.
Yeah, like autocomplete plus. But reasoning, that's about building and testing new plans that work in situations you haven't seen before.
And this ICPC result, especially problem C, seems to lean heavily towards reasoning, wouldn't you say?
I would, yeah. It didn't feel like it just pulled that solution out of a database. It felt like it had to invent it.
Absolutely agree. The model needed what you could genuinely call AI abstract reasoning. To take that flow problem, turn it into an optimization problem, spot the hidden mathematical structure.
So convex shape.
The convex shape, exactly. And then choose the right kind of search algorithm that would actually finish in time. These skills, if you think about it, they're precisely what scientists do all the time.
How so?
Well, defining tractable variables, choosing the right mathematical representation, exploiting geometry or symmetry, verifying with careful tests. That's the bread and butter of scientific discovery.
Huh. That's a really interesting parallel. So Gemini is exhibiting skills fundamental to science itself.
In a way, yes, which is pretty profound.
But it wasn't all exotic, groundbreaking stuff like Problem C, was it? I heard Gemini also did well on more standard problems.
Oh, for sure. That's important too.
Yeah.
While Problem C grabs headlines, many of the other solutions it submitted were, clean, textbook quality, very solid standard algorithms.
Can you give an example of that sort of crisp ICPC craft?
Yeah, certainly. For instance, it correctly implemented the classic rerouting trick on trees.
Rerouting trick. Okay, sounds technical.
It is a bit, yeah. It's a clever technique you learn in advanced algorithms courses.
Yeah.
It lets you compute the sum of distances from every node to all other nodes in a tree really efficiently in linear time.
So a known but sophisticated technique.
Exactly. It's elegant, efficient, and Gemini just nailed it, implemented it cleanly.
And the significance of that is?
It shows the system isn't just a one-trick pony for weird problems. It can also be a reliable teammate. It remembers the standard toolkit and applies those techniques correctly and efficiently.
Like a good human teammate would.
Precisely. Which, of course, raises the big question for everyone listening.
What does this actually mean for me, the developer, right now? Do I need to be a competitive programmer to use this?
Not at all. That's the crucial takeaway. You absolutely do not need an ICPC gold medal to start benefiting. The workflows, the techniques that produce this result, they translate directly to everyday software engineering.
This isn't just for elite contests, then?
Nope. It's about how we can build software better, faster, more reliably, starting today.
Okay, so paint a picture. What does good Gemini coding look like in practice for, say, a typical developer on a team?
Well, first off, it's not about just getting a huge dump of code you don't understand.
Right. No black boxes.
No. Good Gemini coding starts with you defining clear interfaces and maybe some key invariants, the rules the code must follow. Then the AI can help you explore options. Maybe pick the simplest structure that meets your goals for, say, latency or memory usage or just clarity.
Okay, so it helps with design choices.
Yes.
Yeah.
And strong Gemini coding can deliver a pretty solid first draft of the code, plus the test scaffolding around it.
Test scaffolding, like unit tests.
Exactly. It can even run the unit tests, maybe some micro benchmarks, find failures, and then propose focused patches. It acts like a really, really fast pair programmer who never gets tired or needs coffee.
Ah, okay, I like the sound of that. And what about the best Gemini coding?
The best scenario is when it doesn't just give you code, but it explains the core idea in plain English, maybe with a couple of key invariants you can easily check yourself.
Ah, so it helps with understanding and review.
Totally. That speeds up code reviews immensely and helps everyone maintain high standards. It's not about lowering the bar. It's about moving faster while keeping the quality high.
So the advice for listeners is?
Treat it like a brilliant, incredibly fast junior engineer. Someone who has memorized the entire CLRS algorithms textbook.
The big, thick one.
That's the one. They know all the standard techniques instantly.
Yeah.
But you still need to pair with it. You own the high-level design, the architecture, the really critical decisions.
Deep ownership.
Absolutely. You guide it, do that, and you'll likely ship faster, more complex things without sacrificing quality.
That makes a lot of sense.
And broadening out just a little. AI competitive programming, it's more than just a cool benchmark. It's actually a really good, scalable way to measure AI reasoning under pressure.
A proving ground, almost.
Exactly. And the skills that win here, modeling complex systems, choosing the right representation, searching big solution spaces, effectively, these are precisely the skills scientists need every day in the lab.
So the connection to science we talked about earlier, this is a way to hone those skills in AI.
I think so, yeah.
Mm-hmm.
It pushes the AI to get better at things that are directly useful for scientific discovery and engineering.
So you can imagine using this level of AI coding to help with things beyond just software, like designing experiments.
Absolutely. Or running complex parameter sweeps for simulations, but in a way that respects real-world physical constraints. Tasks that used to be just scribbles on a whiteboard might become things AI can actively help structure and execute.
That's a huge potential accelerator for science and engineering.
It really is.
Okay, but we need a reality check here. It didn't solve everything, right?
Crucially, no. Let's be very clear. Two problems, B and G, remain unsolved by Gemini in the contest.
And that's important because?
Because it shows this isn't magic. Reasoning isn't suddenly a solved problem. AI isn't infallible. It shows a system that's incredibly capable, yes, one that can generalize and recover from mistakes, but it still has limitations.
Yeah.
We're not at AGI yet.
Right. And there are practical questions too, aren't there, for engineers wanting to use this?
Oh, definitely. How much compute power does sit behind a result like this?
Ah.
Is it something practical for everyday use? How reproducible are these solutions? If you run it again, do you get the same answer?
And the big one, how do you detect errors before you ship code to production, especially subtle ones?
Exactly. Engineering, at its heart, is the art of controlled doubt. We need to be skeptical. And Gemini coding, or any AI coding assistant, needs to inherit that same rigorous, skeptical mindset.
We can't just blindly trust it. Never.
And we should also expect the game to change. ICPC problem setters are smart. They'll adapt. They'll create new problems that push beyond current capabilities, likely demanding even deeper forms of abstract reasoning from AI. The goalposts will keep moving.
Which drives progress, I suppose.
That's the idea.
So all this points towards, well, it sounds like a partnership model, doesn't it? Human plus AI.
Absolutely. It suggests a collaboration playbook that really works.
Okay, what does that playbook look like?
Well, think about the strengths. Humans bring intuition, that background knowledge or priors about a problem, and crucially, the common sense to know when an approach just isn't working and it's time to stop chasing a bad path.
Knowing when to quit is important.
Very. The model, on the other hand, brings incredible breadth, perfect recall of techniques, data structures, algorithms, and infinite patience. It can try 5 different reasonable approaches without getting frustrated or having its ego bruised.
No ego. That's a plus.
Definitely. So, a really productive pattern we're seeing emerge is this.
Okay, lay it out for us.
1. The human sets the stage. Define the interface, define the requirements, clearly state what done looks like.
Got it. Set the goals.
2. The model proposes maybe 2 or 3 different plans, explicitly outlining the trade-offs of each. Speed versus memory, simplicity versus features, etc.
Okay, present options.
3. The human chooses the best plan, maybe adds some specific edge cases they thought of, tightens the constraints if needed.
Human makes the key decision.
4. The model does the heavy lifting, implements the chosen plan, writes the tests, iterates based on test results.
AI executes.
And 5. The human owns the final review. They have the last say, ensuring quality, maintainability, and correctness.
The human is the ultimate gatekeeper.
Exactly. It's a true partnership. And interestingly, in the ICPC run, if you imagined a combined human plus model team using this kind of workflow, they likely would have solved all 12 problems.
Oh, all 12.
Yeah. So that combined approach is a really useful North Star for teams building real products right now.
Okay, this is super practical. So for our listeners, how do they actually get this value from Gemini coding starting, say, tomorrow? What are the habits?
Great question. We have a few concrete, actionable things you can try. First, write the spec first.
The specification before any code.
Yes,
Okay.
just 2 paragraphs, plain English. What are the inputs? What are the expected outputs? What are the failure modes? Feeding a clear spec like that to the AI assistant dramatically improves the quality of what you get back.
Okay, clarity up front. Makes sense. What's next?
Second, name the tools. Tell the AI the specific library, the version you needed to use. Don't let it guess or pick something obscure.
Be specific about the environment.
Exactly. And if it suggests an algorithm, ask for one you'd feel comfortable teaching a new hire. Clean, standard, well-understood approaches almost always beat clever, obscure tricks in the long run for maintainability.
Good point. Keep it simple and standard where possible. Third habit.
Third, ask for tests before code.
Tests first, like test-driven development.
Kind of. Getting the unit tests up front helps frame the problem clearly for both you and the AI. It reduces that back-and-forth clarification loop, and often the AI writing tests will surface edge cases you might have missed in your initial spec.
Using tests to refine the requirements. Clever.
No.
Okay, and the last one.
Fourth, force trade-offs. Don't just accept the first solution it gives you. Ask for 2 different designs based on clear constraints.
Like how?
For example, give me one design that minimizes memory usage and another that minimizes latency. Then you look at the options and make the strategic choice based on your actual needs.
So it keeps the AI honest and keeps you in the driver's seat for design decisions.
Precisely. You remain in control. Do these 4 things consistently.
Write the spec, name the tools, test before code, force trade-offs.
Exactly. With that kind of discipline, the AI assistant stops being just a fun toy or a novelty. It becomes a powerful lever, a tool that genuinely amplifies your capability and your team's output.
A lever, not a toy. I like that.
Yeah. And stepping back for a final thought, the bigger picture here isn't just about one contest. Remember, the same underlying system also got gold-level results at the International Mathematical Olympiad earlier.
Right, the math competition.
And now this convincing live run at ICPC. Both wins hinged on AI that can actively build plans, test them, learn, adapt, that pattern, that trajectory. It suggests more than just a couple of flashy headlines. It suggests a method, a new way AI is learning to tackle hard problems.
A systematic approach to AI problem solving.
I think so.
So the challenge to you, listening right now, what does this all mean for you? Maybe set aside an afternoon this week. Pick a real problem from your backlog. Maybe a bug that's been annoying you, an optimization you keep putting off, that one-off data pipeline you need.
Just try it out.
Yeah. Write a tight spec for it. Use that collaboration playbook we discussed. Pair with Gemini coding. Insist on good tests. And see if you can ship something that actually matters to you or your team.
You could even start with some of the specific techniques we mentioned.
Good idea. Like what?
Maybe try asking it about that convex search idea if you have a problem that looks like finding the minimum of something smooth. Or the rerouting trick if you're doing calculations on tree-like data.
These are things Gemini demonstrated it can handle well.
Exactly. They're high-leverage moves it can likely execute pretty reliably, giving you a quick win and a feel for the process.
It's a great starting point.
And remember, the real shift, the real impact of all this, it probably won't be felt in a big announcement or a news headline.
Where will it be felt?
It'll be felt in your code repository, when your code reviews get shorter and easier, when the disks you commit are cleaner, more focused, when your production metrics graph gets just that little bit steadier, more reliable. That's the real payoff.
The day-to-day improvement.
Exactly. So the final thought is, try plugging Gemini coding or tools like it into your actual workflow. Measure what changes, see what works for you, share what you learn. That's how we all get better at this together.